Hello friends, good afternoon and welcome to EduSat Live Lectures. Dear friends, as you know that we have started a series on polynuclear hydrocarbons and heterocyclic compounds, and today we have brought yet another lecture in the same series. In today's lecture, we will try and understand the heterocyclic compound called furan. We will try and understand its preparation, structure, chemical and physical properties. To discuss this topic, we have thus our subject expert Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you so much, ma'am. Hello viewers, in the series of polynuclear hydrocarbons in heterocyclic compound, today I will discuss about the furan. It's a heterocyclic compound. I will discuss about its preparation, how can we prepare furan in different ways, its physical properties and chemical behavior also. Today's lecture outline are introduction, nomenclature of heterocyclic compound, occurrence of furan, furan as a resonance hybrid, structure of furan, preparation, physical properties, then electrophilic substitution reaction, in which I will discuss about the nitration, sulfonation, halogenation, Friedel-Crafts reaction. Another reaction includes Diels-Alder reaction, reduction, Gattermann reaction, mercuration and Gomberg reaction. Introduction about heterocyclic compound. How can we define heterocyclic compound? Heterocyclic compounds are relatively stable ring compounds in which one or more ring atoms are of elements other than the carbon, called heteroatom. It can be one atom, it can be more atoms, same atom or different atom. These heteroatoms are mostly nitrogen, oxygen, sulfur elements like phosphorus, boron, silicon, tin, aluminium, arsenic, copper are also occasionally incorporated in the ring. Epoxides, for example ethylene oxide, lactones also known as butyrolactone are generally excluded due to the relative instability of their ring system. Their names may be given after the heteroatoms present in the ring. Thus we have oxygen heterocycles like furan, pyran, etc. Heterocycles like pyrrole, pyridine, piperidine, etc. Sulfur heterolikes thiophene, thiopyridine, etc. for single heteroatom containing compounds. They may also be classified on the basis of size of the heterocyclic ring present. For example, 5-membered ring heterocyclic compound like furan, pyrrole, thiophene, etc. 6-membered heterocycles, for example pyridine. 5-membered rings containing one single heteroatom, for example you can see this is pyrrole, a 5-membered ring. Its common name is pyrrole while IUPAC name is azole. Oxazole, it is furan and oxazole is IUPAC name. Thiophene, thiol, tetrahydrofuran, and you can see this is what? Pyrrolidine, in which you can see there is no pi bond, it is pyrrolidine. IUPAC nomenclature for pyrrolidine is azolidine and for tetrahydrofuran it is oxolane. 6-membered ring you can see containing single heteroatoms. Here are 5 structures you can see. First of all is pyridine, its IUPAC name is azine. This is piperidine, perhydrazine, this is gamma pyran, 4H oxane, gamma thiopyran, 4H thiane, tetrahydropyran oxane. 5-membered ring, this is third category of classification containing 2 or more heteroatoms. This suffix azole is used for 5-membered rings containing 2 or more heteroatoms other than one nitrogen atom. You can see this is pyrazole, or we can also say 1,2-diazole. This is imidazole, IUPAC nomenclature is 1,3-diazole. This is 1,2,3-triazole. This is oxazole. This is thiazole. IUPAC nomenclature for oxazole is 1,3-oxazole. For thiazole it is 1,3-thiazole. 6-membered ring containing 2 or more heteroatoms. You can see one is temporarily nitrogen. Common name for this structure is pyridazine or 1,2-diazine. This is pyrimidine, 1,3-diazine. This is pyrazine, 1,4-diazine. Symmetrical triazine, this is 1,3,5-triazine. This suffix azine is used for 6-membered rings containing 2 or more heteroatoms. Next category for classification is condensed heterocycles. As the name suggests, the rings are fused together or condensed together. Occasionally we have condensed heterocycles containing 2 or more fused rings. The fused rings may be partially carbocyclic, in which only carbon atom is there, no heteroatom is there, and partially heterocyclic, cyclic, in which heteroatom is there. For example, indole, benzofuran, carbazole, quinoline, isoquinoline, etc. or completely heterocyclic, for example, purine. Recently, heterocyclic compounds have been given class name which symbolize their chemical behavior. For example, heteroparaffins. Examples are pyrrolidine, tetrahydrofuran, piperidine, etc. resembles to paraffins, that is why they are also known as heteroparaffins. Whereas heteroaromatics, for example, pyrrole, furan, thiophene, pyridine, etc. resembles to aromatic compound. You can see these structures. This is indole, this is quinoline, and you can see this circle, dotted circle, it represents in indole as well as in quinoline carbocyclic part. Here you can see these are the benzofuran, isoquinoline, carbazole and purine, and this part, dotted part, denotes heterocyclic part because of the presence of heteroatom oxygen, and here you can say nitrogen. Again here you can see nitrogen. This is partially heterocyclic because only one ring contains heteroatom. This is completely heterocyclic as both the ring contains heteroatom in its ring system. Next topic is nomenclature of heterocyclic compound. Very important part. The systematic names for monocyclic compounds are given by using prefixes for the nature of heteroatom or atoms present in the ring. How can we give nomenclature? By dropping a whenever necessary. For example, oxa for oxygen, thia for sulfur, aza for nitrogen, sila for silicon, phospha for phosphorus, etc. If 2 or more similar heteroatoms are present, then we can use the prefixes di, tri, etc. Use, for example, triaza, trioxa, etc. If heteroatoms are different, then numbering start from the heteroatom of the highest group in the periodic table. That is, the atom present in the highest position in periodic table in a group will get the highest number, and as low as atomic number when in the same group. So, if 2 or more heteroatoms present in a group, then the priority goes to the first priority goes to the or low priority goes to the atomic number, low atomic number. Thus, the order of naming will be oxygen because it is having the low atomic number, then sulfur, then nitrogen, then phosphorus, then silicon. We have to see group as well as the other atoms within the same group according to the atomic number. For example, oxa, za, oxygen, then nitrogen. Oxa for oxygen, aza for nitrogen. When both the atoms are present, then we can say oxa, za. The size of the monoheterocyclics is indicated by suffix ol for 5-membered ring, ein for 6-membered ring. In monoheterocyclics, numbering is given in such a way that the heteroatom gets the lowest number and proceeds within the ring anti-clockwise. When the heteroatoms are different, numbering is given in according to the priority level as we have discussed and proceed round the ring in the order of precedence. In common names, Greek letters denote the position of substituents. For example, you can see over here 5 structures are here. First of all is pyridine. The number starts from nitrogen heteroatom. So, we go through the anti-clockwise 1, 2, 3, 4, 5, 6, and these are the common names. Greek letters alpha. These two positions are same, chemically same with respect to this nitrogen. That is why it is alpha and alpha dash. Same here for 3 and 5, beta and beta dash, and with respect to this, this will be gamma. This is furan. Again you can see start from 1, 2, 3, 4, 5, alpha, alpha dash, beta, beta dash. This is imidazole. You can see the number start from this nitrogen 1, 2, 3, 4, 5. This is oxazole. Again because of this group, oxygen start with 1, 2, 3, 4, 5. Heterocyclic compounds 1, that is we are defining the other nomenclature for these kinds of compound in which radical derived from the pyrrole, furan and thiophene by the replacement of one hydrogen are known as pyrrole, furyl and phenyl respectively. Pyrrole for pyrrole, furyl for furan and phenyl for thiophene. Here you can see the examples. The position of hydrogen replaced is indicated by the number assigned to that carbon. You can see this is 2 pyrrole because this group is attached to this position number 2. 2 furyl, 2 phenyl, 2 thionyl and 3 furyl because of these positions 2, 3 and 3. The radicals derived from the corresponding methyl derivatives by the replacement of hydrogen are also known as pyrolyl. You can see this is pyrolyl. Why it is 2? Because replacement takes place at position number 2 with respect to this nitrogen. This is 2 for furyl and this is 3 for furyl as substituent occupied on position number 3. This is 2 phenyl, 3 phenyl. Exception: when we look the nomenclature for quinoline and isoquinoline and does not get the lowest number in isoquinoline, here the number start from this according to the quinoline and then this 1, 2, 3, 4, 5, 6, 7, 8 and quinoline same numbering start from the heteroatom, that is N. Now furan. What is furan? The IUPAC nomenclature is oxacyclopenta 2,4-diene or furfuran. Furan derivatives is named from fur. It is a Latin word from bran because its aldehyde furfural is prepared by distilling bran with hydrochloric acid. What is bran? This is agriculture waste. It contains one oxygen ring in its ring. The position of side chains or substituents are indicated by Greek letters or numbers and one number given to the heteroatom. There are 2 monosubstituted derivatives of furan, 2 or alpha, 3 or beta. Similarly, there are 4 disubstituted products 2, 3 alpha beta, 2, 4 alpha beta dash, 2, 5 alpha alpha dash, 3, 4 beta beta dash. You can see here also the position of alpha beta with respect to this oxygen and this is the structure of furan. 5-membered ring containing one heteroatom, that is oxygen, and oxygen with 2 lone pair of electron and it will have the position number 1. So numbering start from this heteroatom, that is oxygen. Next point, occurrence of pyrrole, furan and thiophene are the 3 simple 5-membered heterocycles. Pyrrole occurs in coal tar whereas furan is present in pine wood. Thiophene occurs in coal tar and shale oil. Naturally occurring compounds like chlorophyll, hemine, cyanocobalamin, vitamin B12, auxins, alkaloids, etc. contain pyrrole ring system in its structure. Now the resonance structure or resonance hybrid of furan. Furan behaves as a resonance hybrid of following 5 resonating structure. You can see these are the following 5 resonating structure. How these form? You can see when these lone pair of electron delocalize within the ring, they can delocalize like this. Here you can see when it donates to this, it will acquire a positive charge and you can see the delocalization from this to this. Again, 5 possible resonating structures are possible. It has a resonance energy of 71.1 to 96.2 kJ mole inverse. Since to be aromatic, a monocyclic molecule must be planar and should have pi electron according to the Huckel's rule, that is 4n plus 2 pi electrons. Out of the 6 electrons needed for this purpose, 2 electrons are the lone pair of electrons from oxygen. as evaluated from its NMR data, that is nuclear magnetic resonance, furan is less aromatic than benzene. How can we conclude that it is less aromatic according to the NMR? Because of shifts. These are shifted from its position as they found in the benzene ring. So, it is less aromatic than benzene. The structure of thiophene resembles furan more closely since in this case also there is an unshared pair of electron in sigma sp2 orbital. Canonical structures carrying no charge are more stable than those carrying charges. Among the charged structures, larger the charge separation, less stable is the canonical structure. In the orbital picture of furan, each atom of the ring, that is carbon or oxygen, both are sp2 hybridized to form 3 sp2 hybrid orbital which are involved in sigma bond formation. Each carbon atom forms 3 sigma bonds lying in a plane are inclined at 120 degree. Oxygen atom forms 2 sigma bonds. In its third hybrid orbital has a pair of electron which is left unshared. Furan ring is more reactive than benzene. This is because of donation of oxygen lone pair, as a result of which furan ring becomes activated. Now, structure of furan. Like pyrrole, furan and thiophene also have structures with flat pentagonal ring. You can see this is flat pentagonal ring, 5-membered ring, 5 atoms are there, involving sp2 hybridized carbons and heteroatoms. You can see in furan there is oxygen atom. So, all the 4 carbon atoms 1, 2, 3, 4 and 5th oxygen atom all are sp2 hybridized with cyclic pi electron clouds containing a sextet of electrons lying above and below the plane of the ring. What we are saying? You can see here pi electron cloud, this is ring, pentagonal ring, a pi electron cloud above ring and pi electron cloud below ring. How it forms? We are discussing here. Of 3 sp2 hybrid orbitals of oxygen or sulfur, 2 have odd electron each while third has a pair of electron. The unhybridized p orbital also has a pair of electrons. The heteroatom oxygen forms 2 sigma bonds with the 2 adjacent carbon by overlapping of sp2 hybrid orbitals containing odd electrons. Here we are talking about that this carbon atom has 3 sp2 hybrid orbital. One is overlapped with the another sp2 hybrid orbital of this carbon atom. Second one, sp2 hybrid orbital having overlapping with this carbon sp2 hybrid orbital overlapping. Third, sp2 hybrid orbital overlapped with this 1s orbital of hydrogen atom, leaving behind this unhybridized p orbital which is having 1 electron. Same here also, same here, same here. The heteroatom forms 2 sigma bonds. You can see this is the heteroatom oxygen. It is forming 2 sigma bond, one from this right carbon, another sigma bond with this left carbon. With the 2 adjacent carbons by overlapping, how it forms? Simply by the sp2 hybrid orbital when overlaps with sp2 hybrid orbital of this carbon and another sp2 hybrid orbital of oxygen overlap with sp2 hybrid orbital of this carbon containing odd electrons. The pair of electron in its third sp2 hybrid orbital of the heteroatoms remains unshared, but the unhybridized p orbital containing 2 electron forms a part of delocalized electron cloud by sideways overlapping with the p orbital of carbon. You can see this is contains a lone pair of electrons, so it makes a sextet of the ring, hence it is aromatic in nature according to the Huckel's rule. While this orbital contains a lone pair of electron will not participate in delocalization and is orthogonal in nature, so it reside on the oxygen atom. This is the orbital picture of furan showing the pi electron cloud above and below the ring. Now, NMR spectra, nuclear magnetic resonance spectra of heterocyclic compound. What it shows? It shows the position of equivalent proton for this carbon, Position of equivalent proton in NMR spectra shows the aromaticity and the comparative study with respect to benzene. because of the inductive effect of the heteroatom. It can be oxygen, it can be sulfur, it can be nitrogen, but here we are talking about furan and we are comparing with other ring also. Ring protons have tau values very much shifted downfield compared with the corresponding aromatic compound due to the inductive effect, or we can say the electronegativity of these atoms. And this downfield shift is more pronounced for hydrogen in alpha position. That is, we are talking about the tau values. You can see this is furan, and when we are talking about the position of these proton or the proton attached to this alpha carbon, these proton resonates as this position 2.62 and beta proton resonates at position 3.70. You can compare with thiophene, you can compare with pyrrole. Here you can say the value is 2.81 for alpha carbon, for beta carbon this is 2.96. For pyrrole, alpha carbon protons, equivalent proton resonates at 3.40, that is 1 proton over here, and beta proton 3.91. For pyridine, you can observe 1.50 for alpha, for beta 3.02, for gamma 2.64. This is another molecule. You can see the resonating field 1.23 for this proton, for this 2.62. Because of these two electronegative nitrogen atom, you can see the tau value is 0.74. So, tau value shifted to downfield because of these heteroatom, because of the electronegative effect, or we can say inductive effect. Now, preparation of furan. First preparation, furan is obtained by distillation of pine wood. By dry distillation of mucic acid gives furoic acid first of all, which when heated at its boiling point yield furan. Here is the representation of reaction. You can see this is the structure of mucic acid, COH, COH, and on heating it will give you furic acid. That is, cyclization is there. Furic acid is what? Nothing but furan with carboxylic acid. On heating it will give you furan. For fural, on oxidation gives furoic acid, which on heating decarboxylates to give furan. Here is the representation of reaction. Furan is most conveniently prepared by decarboxylating furoic acid in quinoline solvent in the presence of copper powder. It is manufactured by the catalytic decomposition of furfural in steam in presence of an oxide catalyst. Here is the reaction. Commercially, it is prepared from agricultural waste, that is rice bran and oat hulls, containing pentasans as shown below. You can see this is the molecular formula of pentasan. On hydrolysis, it will give you aldopentose. And how it dehydrate to give furfural, or we can say ring closure, how it take place, you can see. It can combine to this carbon because of removal of this proton, so we get this furfural. And this furfural decarboxylate, or we can say carbon monoxide, it will give you furan in reaction with calcium oxide or nickel at temperature 350 degrees Celsius. Unsubstituted 5-membered ring compounds can be prepared by heating succinaldehyde with corresponding reagents. Here you can see the different preparations. This is furan derivative. If we see the comparative study, comparative preparation of all these heterocyclics, furan derivative, pyrrole derivative, or this is thiophene derivative. First of all, you can see here, this is 2,5-hexane dione. 2 keto group are there. So, tautomerization can took place. What is tautomerization? Nothing, but there is a transfer of this proton to this keto group. Again, this proton will shift it to this keto group and we will get this enol form. By this enol form with a different reagent, we will get the different product. When we react this with phosphorus pentaoxide at 160 degrees Celsius, we will get 2,5-dimethyl furan. When we react with enol form of 2,5-hexane dione with ammonium carbonate or ammonia at 130 degrees Celsius, we will get 2,5-dimethyl pyrrole, that is pyrrole derivative. And when we react this enol form with phosphorus pentasulfide at 100 degrees Celsius, we will get the product 2,5-dimethyl thiophene. Next preparation is very important preparation, PAL-NOR synthesis. You can see this is acetyl acetone, or we can say 1,4-dicarbonyl compound on heating with phosphorus pentaoxide undergo dehydration to form 2,5-dimethyl furan. The synthesis is called Parnor synthesis. This is in equilibrium with this, in reversible with this product, and it when react with phosphorus pentoxide, it will give you 2,5-dimethyl furan. How it takes place? You can see this is nothing but tautomerization by shifting of this proton to this keto group. Now the comparative study about the physical properties. The melting points, boiling points and dipole moments of pyrrole, furan and thiophene summarized here. This is pyrrole, furan, thiophene, benzene. You can see the difference, the molecular weight, the boiling point, the very first carbon to the heteroatom bond length, second carbon to third carbon to fourth carbon, and in benzene all these bond lengths are equal. It is a colorless liquid, furan, boiling point 305 Kelvin, insoluble in water but soluble in alcohol and ether. It turns a Pines lint moistened with HCl, green in color. You can see high boiling point of pyrrole as compared to furan, thiophene and benzene is due to its molecular association through intermolecular hydrogen bonding. Now very important reaction, that is electrophilic substitution reaction in heterocyclic compound, 5-membered heterocyclic compound. Here is the chart showing the different canonical structure possible when electrophile attacks on position number 2, or we can say position number 5, or we can say position number alpha in Greek letter. Here are the carbocation, this is the intermediate and this will be the product. This is the different carbocation, or we can say canonical structure, resonating structure possible when this electrophile attack to position number 2 or 5. You can see in out of these 3 resonating structure, one structure, that is structure number 3rd, contains a positive charge. These are the canonical structure when electrophile attack to position number 3, or we can say position number beta, and you can say this structure contains positive charge, and this is especially unstable. Why it is so? We have explained earlier also, in previous lectures also, that because of this heteroatom, it is an electronegative atom, so this structure will be highly unstable. The rate controlling step in the electrophilic aromatic substitution is the attachment of electrophilic reagent to the aromatic ring in such a way so as to yield the most stable carbocation. Furan is a resonance hybrid having a large electron density at position number 2 or 5 than position number 3 or 4. Here we are talking about the electron density. During electrophilic substitution, the electrophile is expected to attack at position number 2, this being a center of higher electron density. In practice, 2 substitution is actually favored. Attack at position number 3 gives a carbocation which is a resonance hybrid of structure number 1 and 2, we have seen it. Attack at position number 2 yields resonating structure 3, that is 3, 4, 5 numbering. The extra stabilization conferred on the later hybrid by larger number of resonating structures resulting in a greater spreading of charge, making this carbocation more stable. Hence we can say by looking these structures that 2 substitution will be favored for electrophilic substitution when we are talking about 5-membered ring, that is we are talking about furan. Thank you so much. Hello viewers, we have discussed in the last part that how can we prepare furan, its physical properties. We have compared the other 5 cyclic membered also heterocyclic compound, and we have discussed the general electrophilic substitution in 5 membered ring. Here you can see, if we are talking about furan, we have seen the general mechanism, now particular to the furan. These are the canonical structure we have discussed earlier also. These are the canonical structure when electrophile attack to position number 3, only number 2, and when electrophile attack to position number 2, 3 resonating structures are possible. So, more stable carbocation being a hybrid of larger number of. A intermediate is more stable when number of resonating structure will be large. So, electrophile preferably attack to position number 2. Now we compare the reactivity of different heteroatoms with benzene with respect to benzene. The order of reactivity of these ring system is almost comparable to that of highly reactive aromatic compounds like amines and phenols. You can see the decreasing order of reactivity. So pyrrole is the least reactive, then furan, then thiophene, and benzene is the highly reactive as compared to all these compounds. And these are the resonating structure. You can see highest stabilization energy is because of benzene, thus resonating energy in kJ per mole, that is 150.5, for thiophene it is 117, for furan it is 71, for pyrrole it is 87.8. Now the chemical properties, first of all Diels-Alder reaction. Furan is less aromatic than thiophene and furan and is the only those of which undergo Diels-Alder reaction. Here you can see what is Diels-Alder reaction. When a diene, that is, this is 1,3-diene, or we like a structure, that is, it is a furan, and dinophile. You can see this is the dinophile part of this maleic anhydride. It will give you adduct. A sigmatropic rearrangement is possible, and it is maleic anhydride furan adduct. Next reaction is reduction. On catalytic reduction using ranenical or palladium charcoal catalyst, it forms tetrahydrofuran, which breaks open treatment with hydrogen chloride to form tetramethylene chlorohydrin. You can see how it took place. This is the structure of furan. First of all, reduction is take place, so all the pi bond gets saturated. This is tetrahydrofuran. When react with HCl, it will open, and this part will give you tetramethylene chlorohydrin or 4-chloro-1-butanol. Furan is catalytically reduced to tetrahydrofuran. Here is the reaction, furan plus with ranenical it will give you tetrahydrofuran Tetrahydrofuran is manufactured synthetically from butyne 1,4-diol. Tetrahydrofuran is a valuable solvent the preparation of Grignard reagents. With ammonia it forms pyrrolidine, and with hydrogen chloride tetraethylene chlorohydrin. The furan ring is readily opened under suitable conditions to give 1,4-dioxo compounds. You can see here how the furan ring is opened to this compound when react with HCl and when react with aqueous H2SO4. Next reactions are nitration and sulfonation. Furan is very readily attacked by concentrated acids, and probably the reaction involves the formation of oxenium salt. Attempt at direct nitration with nitric acid mixture and sulfonation results in the formation of resinite products. However, 2-nitrofuran is obtained by nitrating it with acetyl nitrate. 2-sulfonic acid may be prepared by treating furan with pyridines sulfonic acid, that is, sulfonation can however be carried out directly if a group with minus I effect, that is inductive effect, is present in the ring. For example, furoic acid can be directly sulfonated to 5-sulfuric acid. Here you can see this is furan ring. On nitration it will give you 2-nitrofuran. On sulfonation it will give you sulfonic acid, 2-furan sulfonic acid. This is the structure of furic acid. When react with H2SO4, it will give you 5-sulfuric acid. Halogenation. Furan readily reacts with halogens, but polymerization is caused by the halogen acid liberated during the reaction. Because of this difficulty, halogen derivatives of furan are obtained indirectly. For example, furic acid on bromination gives 5-bromofuric acid, which on decarboxylation yields 2-bromofuran. So, this is the indirect preparation of 2-bromofuran from furic acid, not from the furan. First of all, we have done this carboxylation over here. Next reaction is Gattermann reaction. Furan undergoes Gattermann reaction to yield furfural when treated with a mixture of HCN and HCl in presence of aluminum chloride, followed by decomposition of the complex produced with water. First of all, what happens? This HCl and HCN in presence of AlCl3 will give you this kind of complex, and this attack to this furan ring in the presence of AlCl3, and it will give you this product, that is furfural. Friedel-Crafts reaction. Since aluminum chloride attacks to furan ring, a weaker Lewis acid like stannic chloride is used in its place to carry out Friedel-Crafts reaction. Alkylation reaction with furan results in polymerization. So, we are not producing here desired product, then what we can do? So, therefore, Friedel-Crafts is not possible over here. Friedel-Crafts acylation can however be brought about with acid chlorides or anhydrides using stannic chloride as a catalyst. Boron trifluoride in ether has proved to be a better catalyst in acylation with anhydrides. Here you can say acylation of this furan ring with the help of acyl CH3COL, acetic chloride and tin chloride. Acetic anhydride in BF3 also get furan get acylated on position number 2. 2-acetyl furan is the IUPAC name. Next reaction is mercuration. When heated with mercuric chloride in aqueous sodium acetate, furan gives 2-chloro-mercury furan. The mercury group can be readily replaced by bromine, iodine or an acyl group. Here you can see the replacement of this mercury group with halogen and with acyl group, that is RCO. Next reaction is Gomberg reaction. Furan on treatment with diazonium salts in alkaline solution gives aryl furans. Here you can see what happens here. A aryl group introduced at position number 2 with the help of this diazonium chloride. Reaction with N-butyl lithium. Furan when treated with N-butyl lithium gives 2-lithiated furan, which gives the usual reactions of organolithium compound that with carbon dioxide gives furic acid. You can see here, this is N-butyl lithium, C4H9 lithium, this is furan. First of all, you can see here position number 2, lithium, lithium is organopositive, so it will get substituted on this position, and after reaction with carbon dioxide, it will give you furic acid in presence of acid. Lithiation of thiophenes and furans. A reaction that furans and thiophenes do particularly well with fits well with these last two reactions is metallation, particularly lithiation. We have seen earlier also. Metallation of benzene ring is carried out by lithium halogen exchange, a method that works well for heterocyclic 2 as well as we see later with pyridine, or by directed lithiation of CH group next to the activating group such as methoxy group. With thiophene and furan, the heteroatom in the ring provide the necessary activation. You can see how the lithiation took place as position number 2, both in furan as well as in thiophene. So, we are comparing both compounds furan as well as thiophene. These are the general reactions given by furan: Gattermann reaction, coupling reaction, you can see azodike can form, Gomberg reaction we have studied, mercuration we have studied, and the application also. Nitration, bromination, chlorination. In chlorination you can see when we do chlorination at minus 40 degrees Celsius, we will get 3 products together: 2-chlorofuran, 2,5-dichlorofuran, 2,3,5-trichlorofuran. You can see this is sulfonation and this is Friedel-Crafts acylation. Activation is by coordination of oxygen or sulfur to lithium followed by proton removal by the butyl group, and byproduct is the gaseous butane. Here you can see how it took place. These lithium compounds have a carbon lithium sigma bond and are soluble in organic solvents. We shall represent them very simply, but in fact they are typically dimers or more complex aggregates with the coordination sphere of lithium completed by THF tetrahydrofuran molecules. These lithium compounds are very reactive and will combine the most electrophile. In this example, the organelle lithium is alkylated by benzyl halide. Here you can see benzyl halide. How it took place? Treatment with aqueous acid gives the 1,4-diketone. You can see this is the diketone product. Hydrolysis of these two enol ethers. Treatment of this diketone with anhydrous acid would cause recyclization to the same furan, but it can alternatively be the cyclized in the base by an intramolecular aldol reaction to give a cyclopentatrione. Furan is particularly good at Diels-Alder reaction, but it gives the thermodynamic product, that is temperature dependent. The exo product, because with its aromatic dyne the reaction is reversible. You can see the product kinetically preferred product. Here the endo adduct is formed due to the Diels-Alder reaction. This is, you can see, this part is showing the diene part, alternate double bond, and this showing the dienophile part. And this product, that is exo product, is thermodynamically preferred, that is temperature dependent, and kinetically preferred, that is time dependent. Electrophilic addition may be preferred to substitution with furan. Thiophenes and furans look much the same as pyrrole, but there are other reactions in which they behave quite differently. Furan is less aromatic than pyrrole. There is a respect of forming stable bonds such as carbon-oxygen single bonds by addition. This may be preferred to substitution. A famous example is the reaction of furan with bromine in methanol. You can see here. In non-hydroxyl solvents, polybromination occurs as expected, but in methanol, no bromine is added at all. You can see the difference when reacts with methanol and with other solvents, polybromination is took place. Bromination must start in the usual way, but a molecules of methanol captures. The first form cation is 1,4 addition to furan. You can see how 1,4 addition took place because of cleavage of this bromine molecule and delocalization of these lone pair of electrons. The bromine atom that was originally added is now pushed out. How it pushed out? You can see here. This molecule get attached to this because of this positive charge on oxygen. These pi electron adjacent to this heteroatom carrying positive charge get attracted toward this oxygen by the furan oxygen atom to make relatively stable conjugated oxonium ion, which adds a second molecules of methanol. Here you can see another molecular attack in the same way. This product cancels an interesting molecule. At each side of the ring we have an acetal. You can see this structure, this side also and this side also. If we were to hydrolyze the acetals, we would have malic dialdehyde, cis-butene dial molecule. This is too unstable to be isolated. So we cannot isolate these because it is not stable enough to isolate. The furan derivative may be used in its place. The same 1,4 dialdehyde can be made by oxidizing furan with mild oxidizing agent, that is dimethyl dioxyrane. This is dimethyl dioxyrane. You can see in this sequence it is trapped with a Wittig reaction to give an EZ diene, which is easily isomerized to EE. You can see what is the nomenclature for unsymmetrical unsaturated molecule, E for antigigan and Z for zeusaman. You can see how it changes from EZ. This represents EZ diene and this represents EE diene. We can extend this idea of furan being the origin of 1,4 dicarboryl compounds if we consider that furan is in fact an enol other than both sides of the ring. If these enol ethers are hydrolyzed, we would get a 1,4-diketone. You can see enol ether, another enol ether, and this will be 1,4-diketone because of this keto group. This time the arrow is solid, not dotted, because this reaction really happens. The cheapest starting material is the furan 2-aldehyde or furfural, byproduct of breakfast cereal manufacture. Here it reacts with a typical Wittig reaction. You can see the halide because of this positive charge phosphorus and this negative charge methylene group CH2 with stabilized halide. Here you will get this kind of product, that is alkene. Now comes the interesting step. Treatment of this furan with acidic methanol gives a white crystalline compound having 2,1,4-dicarbonyl relationships. Unlike pyrrole and thiophene, furan gives addition reaction with carbene. You can see this is the diazomethane with copper bromide and this kind of addition product, or here this carbene get attached with this double bond. Unlike pyrrole and thiophene, furan is susceptible to undergo oxidation in air, oxygen to form succinaldehyde via furan 2,5-peroxide due to its low aromatic character. You can see how it took place, addition of this oxygen. Here peroxide is formed and then again it will give you succinaldehyde. How it gives test? It gives a red color with aniline and hydrochloric acid. A pine splint moistened with HCl turns green. Uses: as a selective solvent in refining operations, that is clarification of wood resin, separation of butadiene from its mixtures with butene and butane in the manufacture of synthetic rubber, removal of sludge, forming materials from lubricating oil. So, it is very important solvent. As you can see the various applications. As a raw material in the synthesis of adiponitrile via tetrahydrofuran, used in the manufacture of nylon, rubber, in the preparation of furol, furfuryl resins, in the preparation of dyes, azodyes, plastics and malic acid, as a solvent in the manufacture of synthetic rubber, as a preservative for leather and wood, as a reagent in checking purity of ghee also. Now, this is the derivative of furan. It is what? Furfural. First of all, we are talking about furfural. What is furfural? When furan contains a aldehyde group at position number 2. So, it is also known as 2-furan carbaldehyde or 2-furaldehyde. It is also known in IUPAC nomenclature oxacyclopenta 2,4-diene 2-carbaldehyde. How can we prepare furfural? First of all, we can prepare by distilling a pentose with dilute sulfuric acid. You can see this is the structure of pentose with 5 carbon, 3, 4, 5, and with dilute with aqueous H2SO4 it will give you furfural. By treating husk or bran rich in pentoses with dilute sulfuric acid followed by steam distillation. Furfural is manufactured from agricultural waste like oat balls, corn, cobs, etc. by tree with hot dilute sulfuric acid followed by steam distillation. The pentasens polymer that are anhydride derived from pentoses or hydrolyzed by sulfuric acid into pentoses which then dehydrocyclization to give furfural. So, here you can see the preparation of furfural. This is the molecular formula for pentosan. It will give you first of all pentoses, then on acyclization you can see how dehydration took place with this, and we will get the product furfural in 100%. Now, the physical properties of furfural. Furfural is a colorless oily liquid, boiling point 435 Kelvin, which closely resembles benzaldehyde. Chemical properties: furfural resembles benzaldehyde because it contains the aldehydic group at position number 2. It undergoes usual electrophilic substitution reactions to give mainly 5 substituted derivatives under suitable conditions. Use of strong acids and oxidizing agents must be avoided. Here you can see these are the electrophilic substitution reaction chart showing. This is the furfural. First of all, oxidation with KMnO4, that is potassium permanganate, or silver oxide, that is Ag2O. It will give you furoic acid. What is furoic acid? It is nothing but furan 2-carboxylic acid. That is, this aldehydic group get converted to this carboxylic group. Next, oxidation. Oxidation with sodium trioxygen chloride. It will give you fumaric acid. You can see this is the structure of fumaric acid. Then reduction, copper oxide or chromium ditrioxide. It will give you furfuryl alcohol. Next, reduction with nickel, catalytic reduction. You can see this is the structure of tetrahydrofurfuryl alcohol. That is, addition of hydrogen atom on these unsaturated carbon. Next reaction is Cannizzaro reaction with NaOH. It will give you furoic acid, and this is furfuryl alcohol. Another reactions, electrophilic substitution reaction for furfural. These are the benzoin condensation. Benzoin condensation took place with potassium cyanide. You can see this is furfuron. Here you can see the carbonyl group, and this is alcoholic group at this carbon. Next reaction is the Perkin reaction with acetic anhydride and sodium acetate. It will give you furyl acrylic acid and acetic acid. With Claisen reaction, it will give you furfuryldene acetone, and with decarbonylation, it will give you furan with zinc chromium tetroxide or manganese tetroxide chromium. Oxidation and reduction. On oxidation with silver oxide, furfural yields furoic acid, while on reduction it yields furfuryl alcohol. You can see the reaction. This is the structure of furfural. On oxidation it will give you furoic acid, that is, this aldehyde group get converted, get oxidized, that addition of oxygen. How can we judge that there is oxidation or reduction? Simply, if addition of oxygen took place, then it is oxidation, or elimination of oxygen took place, then it will be reduction, or we can say elimination of hydrogen, or elimination of hydrogen is oxidation, or addition of hydrogen is reduction. Increase in oxidation number is oxidation, decrease in oxidation number is reduction. Release of electron is oxidation, addition of electron is reduction. So, here we can define oxidation and reduction in 5 different ways. You can see oxidation took place over here, addition of oxygen, this is furoic acid, and here you can see the addition of hydrogen took place at this aldehyde group or carbaldehyde group, and you will see this is the furyl alcohol. Furfuryl alcohol. Cannizzaro reaction with aqueous sodium hydroxide, furfural forms furfural alcohol and sodium salt of furoic acid. With ammonia, furfural reacts with ammonia to form furfuramide. You can see this is the furfural and this is the furfuramide. For example, when react with benzaldehyde. With alcoholic KCN, potassium cyanide, furfural gives furan, which on oxidation gives fury, that is benzoin condensation, which on oxidation gives benzyl. We can compare with this condensation also. Perkin reaction, furfural undergo Perkin reaction, that is on treatment with sodium acetate and acetic anhydride, it gives furyl acrylic acid. Here you can see what happens here in the reaction. Claisen condensation, first of all we will get this furan, and this on oxidation, that is removal of this hydrogen, will give you furyl, the final product. With ethanolic potassium cyanide, furan is formed, and this on oxidation gives furyl. When heated with potassium hydroxide, aqueous potassium hydroxide, furyl gives furylic acid. It is called benzylic acid rearrangement. Furfural reacts with aniline to form an anyl. It is oxidized by sodium chloride to fumaric acid. Furfural condenses with dimethyl aniline in the presence of zinc chloride to form furfuraldehyde green. A characteristic reaction of furfural is the red color. It gives aniline and hydrochloric acid. It also turns green a pink color. So, in this way we have discussed about the preparations of furan, its physical properties and its chemical behavior. We have compared all the 5-membered ring with thiophene, with pyrrole. We have discussed all these reactions. Hope you understood this lecture. Thank you so much.
Dear friends, it is our continuous knowledge enriching lectures, and we hope that with today's lecture you have come to understand the heterocyclic compounds that we have been discussing. On that note, I would like to thank ma'am for this discussion, and we hope that you have come to understand and you have come to like today's lecture. On that note, thank you dear friends for watching our show. Stay tuned and keep watching. Thank you.